Lesson: Overfitting and regularization in deep networks. Overfitting is one of the most common challenges faced when working with deep neural networks. It occurs when a model learns the detail and noise in the training data to an extent that it negatively impacts the model's performance on new data. This happens when the model is excessively complex, with too many parameters relative to the amount of training data. The model essentially memorizes the training data rather than generalizing from it, leading to poor performance on unseen data. Regularization techniques are crucial in addressing overfitting, helping to improve the model's generalization ability. The concept of overfitting can be better understood with the example of a polynomial curve fitting problem. Consider a scenario where you have a dataset of points that approximately lie on a curve. A simple model might fit a straight line through these points, capturing the general trend but missing some nuances. A complex model might fit a high-degree polynomial that passes through every point exactly. While the complex model might seem more accurate on the training data, it is likely to perform poorly on new data because it captures noise rather than the underlying pattern. In deep networks, overfitting is exacerbated due to the large number of parameters and the high capacity for modeling complex functions. To mitigate this, regularization techniques are employed. One of the most widely used regularization techniques is L2 regularization, also known as weight decay. L2 regularization discourages the learning of large weights by adding a penalty term to the loss function proportional to the square of the magnitude of the coefficients. This encourages the model to keep the weights small, which in turn helps in reducing the model complexity and thus overfitting. Another popular regularization technique is dropout, which was introduced to address overfitting in large neural networks. Dropout works by randomly dropping units along with their connections from the neural network during training. This prevents the units from co-adapting too much. During testing, all units are present, but the outgoing weights of each unit are multiplied by the probability of that unit being retained during training. This technique has been shown to significantly reduce overfitting and improve the performance of neural networks on a variety of tasks. In practice, implementing dropout is straightforward, especially when using frameworks like TensorFlow or PyTorch. For instance, in PyTorch, you can add dropout to a layer by simply including nn.dropout, where p is the dropout probability. This effectively means that during each training iteration, 50% of the neurons will be randomly set to 0. By integrating dropout into neural network architectures, practitioners can significantly enhance model robustness without sacrificing flexibility. Beyond these traditional methods, data augmentation is another practical and highly effective strategy to combat overfitting. By artificially expanding the dataset through transformations such as rotations, translations, and flips, the model can be exposed to a broader variety of inputs without needing more labeled data. This is especially useful in domains like image classification, where acquiring additional labeled data can be expensive and time-consuming. Libraries like Keras in TensorFlow offer comprehensive tools for data augmentation, allowing users to easily apply these transformations during training, thereby improving generalization. Regularization can also be approached from the perspective of architecture design. Convolutional neural networks, for example, inherently reduce overfitting through their shared weights and spatial hierarchies that capture local patterns effectively. Using pre-trained models and fine-tuning them for a specific task is another way to leverage regularization. This transfer learning approach not only saves computational resources, but also benefits from the regularization effect of the pre-trained model weights, which have been learned from massive, diverse datasets like ImageNet. While regularization techniques are essential, it's equally important to adopt a comprehensive validation strategy. K-fold cross-validation is a powerful technique that involves partitioning the data into K subsets, training the model on K1 subsets, and validating it on the remaining one. This process is repeated K times, with each subset used exactly once as the validation data. The results are then averaged to produce a single estimation. This method provides a robust indication of how well the model will perform on unseen data and can help detect overfitting early. Hyperparameter tuning also plays a crucial role in regularization. Techniques such as grid search, random search, and Bayesian optimization can be used to find the optimal values of hyperparameters like dropout rate, learning rate, and regularization strength. Automated tools such as Optuna and HyperOpt provide frameworks for efficiently searching the hyperparameter space, allowing practitioners to systematically enhance model performance while minimizing overfitting. Case studies highlight the practical implications of these techniques. For instance, in a Kaggle competition focused on image classification, teams employing advanced regularization strategies like dropout and data augmentation consistently outperformed those that did not. In another study, researchers training a deep neural network for medical image segmentation reported that incorporating L2 regularization and dropout significantly improved the model's ability to generalize to new patient data, thus enhancing its clinical applicability. Understanding the balance between model complexity and data is also critical. According to the bias-variance trade-off, increasing model complexity decreases bias but increases variance. Regularization techniques aim to find the sweet spot where both bias and variance are minimized, thus achieving better generalization. Practitioners must be adept at diagnosing whether a model is overfitting or underfitting and apply appropriate regularization strategies accordingly. In conclusion, overfitting is a critical challenge in deep networks that can be effectively addressed through regularization techniques. L2 regularization and dropout are foundational tools that have proven efficacy in reducing overfitting by constraining model complexity. Data augmentation and architectural strategies further enhance model robustness. Employing a combination of these techniques, along with rigorous validation and hyperparameter tuning, practitioners can develop deep learning models that generalize well to new data. The integration of practical tools and frameworks, such as TensorFlow, PyTorch, and automated hyperparameter tuning libraries, empowers professionals to implement these strategies effectively, addressing real-world challenges and enhancing their proficiency in deploying advanced neural networks.